Okay, so basically what we're going to do today is to try to replicate the exercise that we did yesterday, resorting to D'Alembert's equation, this time using the newly discovered Lagrange equation, in order to see in a practical example how they actually can serve us and in which ways they are somehow faster and easier to implement. Okay, so we are always in the frame of Lagrange equations. And we are going to do an application. Okay, so an example. So let's get back to the drawing that we used last time. Which is this one here. Okay. So if you remember, here we chose the d of the degrees of freedom like so. So we have a rotation theta, and then we have distance parameters of the mass of our body sliding here from the origin. And the name of this coordinate was Q, all right? So since yesterday we saw that in our case, so actually in general, Lagrange equation write as follows. So the derivative with respect to time, this is one way of writing them. So in this case, I'm writing them using kinetic energy. Sometimes it can be more profitable to use the also the potential energy and so the Lagrangian function. So it depends on the application, but they are completely equivalent, as you can easily understand. Right? Oops. So in this case, I didn't do any partition between conservative and non-conservative forces. So in our case, this translates to what? Okay, because we have that basically our Q is the theta angle and then the Q scalar parameter. Okay, so this is our Q vector. And so how does this translate, this equation, in our case? It translates like this. We have a system of two equations, like so. We have the time derivative of what? Of the partial derivative of the kinetic energy with respect to theta dot minus the derivative, the partial derivative with respect to the angle theta. This must be equal to a component, okay, the first component of the, yep. That's what I was actually mentioning at the beginning. So, yeah, correct. So that's T. Yeah. So this is T. This is one of the formulations. We can either use direct kinetic energy or the Lagrangian function, but not both, of course. One of the two. And this must be the first component of the generalized vector of external forces. Okay, so the one associated to the Lagrangian parameter theta. Okay, and formally identical for the other parameter. Okay, so these are the two equations that we have to write. Q, like so. All right, so these are the two equations that we have to write. In order to do so, let's calculate those quantities. So this way. Let's start from, for example, P. Let me just close the door. So we have that P dot. The position we have already seen that could have been written in the previous example. We have seen that this can be written as sinus of theta 0 times Q plus cosinus of theta sinus of theta 0 times Q dot. Okay, this in fact can be written in form of a matrix written like so: minus Q sinus of theta cosinus of theta Q cosinus of theta sinus of theta applied over the vector of generalized coordinates, generalized velocity, sorry, theta dot and Q dot. Okay, so that this in fact can be written as a matrix B, which is this one here, times Q dot. Okay, all right. So if this is true, and it is true, then our kinetic energy, we saw, can be written as 1 over 2 of the mass m of the particle, of our body, times what? P scalar, sorry, P dot scalar P dot. Or, which is the same, we can also write it as, instead of the scalar product, the matrix product but with the transpose. Okay, it's just the same. But why do I use this kind of formulation? Because now, since we know that this is true, we have that this can be written as also 1 over 2 m Q dot transposed B transposed applied over B applied over Q dot. Okay? Okay. And this is very easy to compute. If you do this matrix multiplication, you get the following quantity: 1/2 of m Q dot, sorry, Q square dot theta dot squared plus 1 over 2 of m Q dot squared. Okay? Does this value surprises you? No, right? This is the angular, the kinetic energy associated to the angular motion. This is of the linear motion. So this is the kinetic energy of the mass sliding, along the road, and this is the mass which maintains its relative position with respect to the rod, but then starts rotating. Okay. Okay. So this is the kinetic energy. If this is true, then we are basically done almost. Because we have to then fulfill the kinetic these equations here. Okay, that we have presented before. And so let's do some calculation. We have that d theta over d theta is 0. Then we have that the t over the q resulting to that is m theta dot square q. Then we have that the t over the theta dot is m q squared theta, and the t over the q dot is equal to m q dot, and therefore, since the mass is constant, the t of the derivation of t with respect to theta dot is equal to m q squared theta double dot plus, sorry, let me just write it a little bit, m q squared theta double dot plus 2m q dot theta dot, and on the other hand, the t of the q dot is m q double dot. Okay. Now, the last element that we need in order to be able to complete our formulation. Can I slide? Yeah, go ahead. The last thing that we need is basically the estimation of the components of the generalized forces. Okay, the q theta and q here. So, but this we know, because we know that the delta work of external forces, we have seen it in the previous exercise, if you remember, could be written as q external transpose applied over delta q. Okay. And this was written in the following way, if you remember. T minus m g q cosinus of theta times the theta minus m g sinus of theta times the q. And this, in fact, means that this basically is nothing different than the following. T minus m g q cosinus of theta minus m g sinus of theta transposed applied over delta theta and delta q. Okay? So this means basically that our q theta is this one, the first component of this vector here. You see? So this is t minus m g q cosinus of theta. While our q is minus mg sinus of theta. Okay. Now we have all the elements to write down this equation here. Okay. If you put all together, what you're going to get is the following. Let's write it down. m q squared theta double dot plus 2 m q dot theta dot equals to t minus m g q cosinus of theta. And then we have m q double dot minus m theta dot squared q equal to minus m g sinus of theta. Which are exactly the same that we derived last time. Okay? Of course, they must be the same. But please note the fact that we needed 1/10 of the time to derive this equation. So it was much more mechanic, okay, if you want, much more determined already, the procedure. So you see what is the power of this Lagrangian equation and the Lagrange coordinates. First of all, you have a much easier treatment of the constraints. Secondly, you have a very powerful formulation which is able to deliver just as a, through a derivation, basically, the equations of motion for your system. Okay? So this is a simple case, but yet you can see the difference between the two approaches. Okay? Questions? No, we did. Otherwise, we wouldn't have the same equations. Inertia forces were taken into account through the definition of the kinetic energy. No, because we didn't calculate it directly because this is done basically through this, the introduction of the kinetic energy. Okay. All right. So all of this was something, which is very nice, but, please remember that in this example, we were able to not deal with the constraints directly because we were smart enough to choose the coordinates, okay, the degrees of freedom, so that they automatically define a space of possible configuration which satisfied automatically the constraint, okay? But this is not always possible. When it is not possible, it is not possible when you have, for example, non-holonomic constraints. Okay, when you have non-holonomic constraints, you typically can't directly relate, okay, the coordinates one to the other as a linear combination or nonlinear combination of the others, because what you have to deal with is velocities, not coordinates. Okay, so the coordinates derive with respect to time, and so you are not straightforwardly capable to express the dependent, as a function of the dependent in the independent ones. Okay, you cannot typically always write QD equals to F of the QI. Okay, and this typically was written as, if you remember, like this. We saw it. This is possible only for holonomic constraints. When they are non-holonomic, this cannot be done. So what do we do in that case? Well, we have to deal with another formulation. Okay, so now what we are going to do is to see how to include in the equations of motion the constraints in these two cases, when we have holonomic constraints and when we have non-holonomic constraints. Okay, so Okay. So the first case that we are going to see is the first formulation, which is called embedded formulation. Embedded formulation is valid only for what? So holonomic constraints only. Then we have it's capable to basically express in the minimum set of coordinates. So that's the smallest number possible of equations. Okay, what is the minimum set of coordinates? The independent coordinates, right? So that's the one that you really need to set, the one that you set arbitrarily. So the DOS, right? Then, since they are expressed only in terms of the degrees of freedom, you have no appearance of the constraint forces, and we always make use of the hypothesis of workless constraints here. Okay, so basically we have that the work, not even just the virtual one, but the work of constraint forces is 0. Okay. All right. So what we do is now to start, in order to be able to write this embedded formulation, we start from the D'Alembert-Lagrange formulation. Okay, so let's write it like so. Of Lagrange equation of motion, these formulations here embedded, and then we'll see the other one. We'll always resort to the Lagrange equation, but this you will see. So here we have the one that we already saw. So you see what I'm doing here. I wrote the first part of Lagrange equations for the independent coordinate. Okay, now I'm adding the second part for the dependent ones. So we write exactly the same. Okay. So I just made a partition. Okay. Now we can make two considerations here. So you see now that this L, this Lagrangian functional, is basically a functional of the coordinates and their derivative and of time. Okay? So we can write the following. So we have that L is a functional of what? Q dot, and T, right? But now we have, okay, due to the constraints equations, which are holonomic, remember, we have that Q is basically what? Q independent, and then Q dependent. But the Q dependent is a function of the Q independent, right? And as well for velocities, Qi dot and Q d dot is a function of the Qi dot. So eventually, L can always be reformulated, rearranged, so to be only expressed in terms of the independent coordinates and velocities. Okay? Okay? Since the Q basically are only a function of the independent ones and also the velocity, basically the functional dependence of this functional is only on the independent ones through the coordinate equation, holonomic, because this can be done only for holonomic ones, remember. In fact, this relationship, we saw it already, is the following, no? QD is C di of Qi. Where C di, if you remember, is minus C Q d to the minus 1 times C Qi. CQD and CQi are the Jacobians, are partition of the Jacobian of the system for non-holonomic case. So if this is true, and it is true, you see these equations here, can all be rewritten only in terms of the independent coordinates. So first of all, this is 0. Because this is a derivation of L with respect to the dependent ones. But we just demonstrated that L can be rearranged or to show only dependence with respect to the independent ones. So this is 0. This is 0 as well. The only term which is left is this times this. But this basically can be rewritten in terms of the independent ones. So all of this can be basically put like that. Okay, so you have the following. Then we have minus QE independent, non-conservative transpose plus what? Q non-conservative transpose external dependent ones, okay, the dependent ones, times C. I will put it back, don't you? And all of this multiplied delta Qi. Okay? Something's wrong? Ah, questa? But this we have already, seen a couple of lessons ago. And this is equal to 0. Okay? So you see now that all I have is just the functional dependence on the independent parameters. But since they are independent, and we wanted them to be independent, now we can pass from this formulation, which is a formulation called, as we saw, D'Alembert-Lagrange, to a pure Lagrangian formulation, which we basically remove this part, and we pass from a scalar equation to a vector equation. Okay? So point what? Because these are independent. So if this is true, then this between square brackets must be 0. Okay? So we can call, basically, this part here, we can call it Q transposed external. These are the non-conservative ones. Or we can use B for the body, all of it. Okay. This is a set. Is a set of n minus nc differential equations. And that's the minimum set, the minimum number, okay, that I can arrive to. Okay, I can reduce no more the system than to this minimum set of equations. Okay. So that's basically the best case scenario, if you want. Okay. Yes, because it's n minus nc, where nc, this is the number, as you see, this is the number of parameters. This is the number of the Qs, and this is the number of the constraints. Of independent constraints equation. Okay, so since we need at least n minus nc parameters to be able to determine the configuration of the of the system at a given time t, we need at least n minus nc governing equations that tell you how they evolve in time. Okay? So that's the minimum set. All right. Now we deal with the case where we are less lucky and we have non-holonomic equations. And this is called augmented formulation. Okay. So please note that this is a standalone, so you don't have to put, aside from these equations, the constraints equation. They are already inside this one here. Okay. So all you got is this. That's the best thing you can have. In the augmented formulation, we have, first of all, holonomic and non-holonomic constraints. So this holds for both types. Okay. We always have work-less constraints. So we have this hypothesis here. And so now let's see how we can derive this formulation. All right. Let's see how we can do this. So the first thing is that we start basically from this consideration. So since you have work-less constraints, work-less, yes, constraints. It means that basically, if these are the contact forces, QC transposed over delta Q, which is a variation, okay, of the Q, this must be equal to 0, right? This is by definition. But this means that, what does this mean? Because this could also be written like so, if you remember. Maybe it's more familiar. When the scalar product between two vectors is 0, it means that they are orthogonal, okay? So QC is orthogonal to delta Q. But bear with me. If these contact forces are orthogonal with respect to the possible motions, okay, because this is a virtual, but it can be also non-virtual in general. If this is virtually orthogonal to the possible variation of your configuration, it means they are parallel to what? So if the contact forces are orthogonal to possible motions, okay, it means also, what is also orthogonal to possible motions? Can you guess? So if you imagine the constraints equations, the constraints equation, they do define, if you want, if they're in the two space, it's a surface. If it's more than two parameters, it's an hypersurface. Okay. It means that, bear with me, if this is, for example, you have a constraint in two parameters, like the case we had before. Okay, we have only two parameters. So let's say that you have, okay, so you have, so Q1, Q2, and Q3. Okay? So your constraint equation is typically, if it's done like this, it can be a surface like so. Okay? It can be a surface like this. Okay? So your constraints equation, which you call C, is basically a surface of Q1 and Q2. No? And then you have okay, no, well, Q1 and Q3, and then the second one is actually evaluated. So it means that the Q1 and Q3 in this case are the independent ones. And then you have the third, which is typically, automatically defined with respect to the C. Okay, this is what I'm saying. So in the case in which you have 3 coordinates and your constraint equation is actually basically constraining the third. Okay. What does this mean? It means that your possible motion basically stays here over the surface. Okay. Now, when you do the Jacobian, which is basically the derivative of C with respect to Q, and then you apply it to a whatever vector, you obtain a vector which is normal to this surface. Okay? Because you're doing the derivation. Okay? So if this is true, it means that delta Q leads over this surface, is tangent to this surface. While this vector, which you can call lambda, for example, I think I call it lambda here. Yeah. You call it lambda. This is a vector. It's basically perpendicular to this surface. Okay, for example, here it's like this. Okay, so this is C Q lambda. Okay. Then if QC is perpendicular to the Q, is parallel to this one here. Okay. How is it parallel? It is parallel so that we can write that QC can be written as CQ, which is the Jacobian, applied over lambda. Okay, where this vector here has to be determined. Okay, this is, you could imagine this to be a scalar constant in a, in a scalar equation. This is a vector equation, so this lambda is a vector. But if this was not a vector, you could write this as a scalar value. Okay. Typically, for this kind of equation, this is also implemented with a minus. Okay. Did you get what was the reasoning behind all of this? So if they are both perpendicular to the same surface, they must have the same direction. Yeah. Okay. And this lambda is basically, this is a constant vector, which whose coordinate must be determined. This lambda is called the vector of Lagrange multipliers. Have you ever heard of this? Okay. Okay. Whose coordinate must be determined. All right, why did I do all of this? Because now we do the following. So we can rewrite. So let's do always the partition, because as I was mentioning, the fact that we can do a partitioning between dependent and independent, it is always possible, both for holonomic and non-holonomic cases. What it is not possible for non-holonomic constraints is directly expressing the dependent in terms of the independent, because we have velocities included in this functional dependency. Okay, so it's cannot be directly implemented. So we can write Lagrange equation as follows. So here we have the independent ones again. Now, in addition to what we have seen before, I will write the following quantity. Okay, this is equal to 0. This is the D'Alembert Lagrange. You see, so here is this is dependent one. So these are the contact forces which I've included in our formulation. Why? Even if they are workless. If you think about it, this here times the external and this part here operating over QD is 0 by definition. So I'm not adding anything with respect to what we have seen before. The first step is just exactly the same. Okay. With the position that we have done before, we can write this. Okay. I basically just substituted this thing, the contact forces, with what we have seen before. Please note that, of course, the order is reversed to what we have seen before, because here we have a transpose. Yeah, sorry, here I made a mistake, sorry. I think I forgot something. Yes, it's here. Yes, okay. There's a transpose here, of course. Okay. Okay. All right. Is it hot in here, or it is? I think. All right. Now we can do the following. Just let me open a little bit the door because I think the heating is on. Okay. Now, so now someone can say, okay, but what is the use of all of this? We have just inserted a new vector whose components must be determined. Well, in fact, yes, but Lagrange multipliers are chosen so that the second component, so this one here, is 0. Okay? So this is the overall second part of the previous equation. So the lambdas are set so to satisfy this equation. Okay? If this is true, we are left with so this is only the dependent one. Huh? Okay? This is what we are left with. But now, you see, all of this is written only in terms of the independent coordinates. So again, we can pass from the Lagrange to the Lagrange. Okay? And so we can basically remove this and put this equal to 0 like this. Okay? But you see now, can you see that these two equations are formally the same? The one on top and the one on the center. So if we go back and we basically do the inverse operation, then the partition of Q, so we go back from Qi and Qd to Q, okay? Basically, it means that we can rewrite this in terms only of the Q. So we can write right? All of it expressed in terms of the Q. Okay? So to sum up, and then I will write it in the next slide, let's do the count of how many equations we have. Huh? We have these equations here. And then we have this one here. Okay? Which are the constraints equation, which we have to take into account, because in the other one, they were already inserted implicitly. They were embedded in the formulation. Here, they are not. So how many equations do we have here? So we have here, these are n differential equations. And here we have NC, algebraic equations. These are algebraic equations. You know, the constraints are typically expressed in terms of so we are left with a mixed system. Of, in total, n plus nc differential slash algebraic equations. So previously in the better formulation, we had n minus nc. Now we have n plus nc. Okay? Equations. So you see that the type of constraint matters a lot. Because this, to solve, is not easy. Because you have both differential and algebraic equations. You have to solve them at each iteration. And not only they are mixed, but they are many more than the other one. So if you imagine a system with a lot of constraints for complex multi-body system, this NC here can be very high. So when you have to pass from n minus nc to n plus nc, you have a difference of 2 nc. It means a lot of equations more. Okay? All right. Yes. This is valid for both. If you use this for holonomic, okay, it is always you have always to go through the same formulation. Okay, it doesn't modify the formulation because this is a formulation which you use to solve a problem. Okay, it doesn't adapt. Okay, of course, once you write a code, it's there, right? So it works for both, but it always stays the same. Okay, all right. Esattamente. No, il risultato deve essere ovviamente lo stesso, soltanto che questo è molto più pesante dal punto di vista computazionale e può richiedere più iterazioni per arrivare a convergenza, ok? Quindi non solo è più pesante computazionalmente, ma anche meno efficiente, ok? E tipicamente sono queste le formulazioni che però vengono usate, come il Lagrange multiplier, ok? Cioè sono cosiddette formulazioni, they are typically called penalty methods or the like, because basically you are, you go and at each iteration of the code, you estimate a configuration, a solution, which can infringe, okay, which can go against the constraint to a certain value. And this certain value is basically given by the Lagrange multipliers, okay? And then you try to optimize your solution so that it, satisfies at its best the constraints, okay? So that's why they're also called penalty methods, these ones, okay? But they are more powerful in terms of, really from the theoretical point of view, because they can encompass any kind of constraints, and a priori you don't know which kind of constraint you have. So these are typically, these are the constraints used in the codes, and these are the constraints which are used in Adams, which you will use in your simulations. All right. Now, what we're going to do in the next 20 minutes, if we are able to do so. So this is this is a part of the course, which is this one here now that will start. It's a little bit, heavy in terms of, mathematical formulation, because we have to derive the equations of motion for bodies. Please bear with me, and we will go through it. But the result is very important, and eventually, I'm not sure if we are able to do it today, but if not today, on Monday, we will see the application of the equation that we will derive today, which are called Keynes equations, for the formulation, for the solution of the same problem that we saw. Okay, we solved it with D'Alembert equation, with Lagrange equation. We solve again with Keynes equation, and you see that if with D'Alembert equation we needed 10 steps, with Lagrange equations 5 steps, with Keynes equation we will need 2 steps. Okay, even shorter. So they are useful. Okay, so far we have dealt with particles. Now we will enter the domain of bodies. So okay, we are always talking of rigid bodies for the moment. Then we will also include the elasticity. Okay, in particular, we will deal with Keynes equations. So Keynes equation basically resort all of their power, if you want, for the formulation, on one consideration. Let's see it. So we have that the virtual work could be written as follows. Is the sum from I going not anymore to NP, but to NB, because we are not dealing with particles, but with bodies. And the sum of J going from 1 to N, the number of coordinates, of what? Of, of F I multiplying the partial derivative of P with respect to J, where this F is nothing different than Fe, the resultant of external forces, minus the rate of the momentum. Okay? This is something that we have already wrote. Well, if this is true, and it is true, we can rewrite the following. It's not difficult. Okay? So basically, I pass from positions and generalized coordinates to velocities and generalized velocities. Okay? Now, it seems a very trivial passage, you know, it seems a very trivial step. And in fact, mathematically, of course, it is, but it actually has a quite important consequence. Why? Because you remember that for holonomic coordinates, we have for holonomic constraints, we have that the constraints was written as this. Okay? So in terms of the generalized coordinates, for the non-holonomic case, we had typically this form in terms of the Q, but also the Q dot and T. And this typically could have been written as follows. Okay? Now, you see that, do you remember the difference between holonomic, non-holonomic, and kinematic geometric constraints? So, both of these cases, in fact, can be written in the kinematic form. Okay? So in terms of the Q dot. So while I typically cannot go from here to here, for a non-holonomic case, I can always go from here to here because I can always derive. So this means that I can always go from here to something of this sort. Okay? So this means that I can always express my constraints equation in terms of velocities, right? And so it is very important if in my formulation, instead of dealing with position, I can deal with velocities, because I can always express the constraints in terms of velocities, no matter if they are actually non-holonomic or not, right? So that's a quite smart thing. Because if I do that, if I adopt this formulation, then I don't have to worry anymore if the constraints are holonomic, non-holonomic. I don't care. I derive them if they are holonomic. And I put them into this form. And so with this form, if I deal with velocities instead of positions, then I can include them directly and do the embedding as I did for the embedded formulation. Okay? Do you see the point? So the great difficulty for the holonomic and non-holonomic case that we have just seen, as you know, for the augmented and embedded formulation, is that I cannot typically go from the non-holonomic formulation, which sees the expression of the velocities, back to an expression which sees only the positions, okay, or the generalized coordinates. So from here to here, I cannot go. Instead, the opposite is true. I can always express both the holonomic and non-holonomic in terms of the velocities, because I can always do the derivative. Now, from this consideration, it comes into my mind that if I were able to build a formulation which is only expressed in terms of velocities, that would really benefit me very much, because then I could include, embed the constraints directly in the formulation, no matter if they are holonomic or non-holonomic. Okay? So that's the thinking of Kane. And that's why, for this reason, it started from this consideration. Okay? The expression of virtual work, not anymore in terms of, positions and generalized coordinates, but velocities and generalized velocities. Okay? So that's the key of Kane's equations. So I can always express the constraints equation in terms of the Q's dot. Okay, that's the key point. Now, how am I going to exploit this fact? In the following way. So first of all, in order to better express or enforce the constraint equations, I define what are called motion parameters. I define the motion parameters like this. So I have the generalized velocities Qj, and express the Qj as a linear combination of the motion parameters like so. The generalized parameters, of course, are these ones, are the UM. So you see, what I'm saying is basically just expressing the generalized velocity as a linear combination of other parameters, which I call motion parameters. Why do I do this? For just one reason, because typically when I have this constraints equation, which I have here, this one here, it can be more useful to me to re-express this constraints equation, not directly in terms of the Q dot, but in terms of these motion parameters. okay? It means that I can group parts all together within the constraints equation and simplify their formulation. That's all. You know, there is no rocket science here. I'm just, you know, saying that the Q dot are just a linear, you know, the result of a linear combination of the UMs. That's it.
Looking from horizontally constraints to non-horizontally constraints.
Mm-hmm.
If the constraint is something similar to a constant, so Q1 is equal to 3, Q1.
Mm-hmm.
If I differentiate that, wouldn't I will be being able to information?
No. Why should I do that? I think I already shown this, that you can basically pass from here to here, okay? Given that you maintain one thing. Did you remember when we talked about constraints on the velocities rather than constraints on the actual values? And you know, you remember, I think we implemented the case of a coin rolling over the floor. We saw that they are basically the same, even in the count of Grubler, okay? Given that, of course, you have to take into account this with an initial conditions. But of course, the initial condition is always given for your system. You always have to know how it is initially. Otherwise, you cannot start not even the formulation if you don't know the system at first. If you know that and you enforce this, it's exactly equivalent than enforcing this.
So the constraint is less.
Yes, of course. All right. Now, why do I need the, okay, first of all, let's specify the functional dependence because it's important. We have that the motion parameters, of course, are going to be a function of the Q, of the Q dot, and of time. While these AJM are only going to be function of Q and T, and the same goes for the BJs. So the only dependence on the velocities here is, again, included only in the UMs. Okay. Now, let's do this thing, and then we stop from the definition of total derivative. So the total time derivative, which is P dot for the body I, this is what? The sum of K going from 1 to the number of bodies of the partial derivatives of Pi with respect to the Qk times Qk dot plus the Pi with respect to the T. This is the definition of total differential. So the dependence of P with respect to time is the dependence of P with respect to Q's, which depend on time. And this is the first part. And plus the dependence directly of P on T. Okay? This is the definition of total differential. Therefore, if we use the motion parameters, we can rewrite the following. P dot I is equal to the sum of k going from 1 to the number of bodies of what? Of the Pi with respect to the Qk. Now we have, here we should have had Q dot k, no? But we express it in terms of motion parameters. So we have the sum going from m1 to n, the number of coordinates, of a km um plus bk, and then there is the last part of the total differential, the p I over the t. Okay. Now this can be rewritten as follows. We just have to explicitly write I'm just doing the product, no? Okay. I've just done basically the multiplication. That's what I did. Now I call this one here V. You see here the only dependence, actually not here, not this one here, but all of it. So I can actually, let me exchange the order of these two sum. Okay, it's just the same, huh? So let me write D here M, and this goes to N, and here K, and then it goes like this. Huh? It doesn't shock you, this one, right? I just reverse the order of the sum. So this one here I call it Vm with the overhead I. You see, because this is, of course, the sum over the k over k. And when I do the sum over k, of course, the index, the subscript k vanishes. So it only has a dependence on the index m and I. All right? And that's why I have Vmi here. The same goes here. And this one here I call Vi over at t. Please note that this is not an index t, it's just a subscript, okay? So this is not an index, this t here. It's just a subscript which I'm calling because I'm writing because there is a partial derivative with respect to time. That's it. Okay, I'm not summing anything. So this can be written, finally, as the sum of m going from 1 to the number of particles of this Vm over at I um plus V over at Ti. Okay? So what I've done so far is, is nothing than rewriting the velocity of the particle. taking into account the motion parameters. That's it. Now, what we're going to do probably next time, just because we are done, is to introduce another form of parameter which are called the partial velocities. And these partial velocities will be able, with these partial velocities, we will be able to rewrite the equations of motion in terms of velocities as we wanted. And so we will be able to encompass all forms of constraints equations within our formulation. No matter what constraints is there, then we can treat it. And that's the powerful, feature of these Keynes equations. We will see it next time. Okay. And then we will implement, again, the exercise that we've seen, and you'll see that we will resolve it in 2 passages, and that's it. I'm sorry? Sure. Well, that's the total derivative. Okay. Okay, that's it.